Okay. The rest of chapter 18 is about the consequences of the conclusions of the kinetic theory of gases. Section 4 is a section that I would like to, go over, but I don't want to do it yet because I think it makes more sense after some of the ideas from chapter 19. So I'm actually going to skip ahead to chapter 19. And I'm actually going to pull some things out of chapter 19 for us to cover now. Next week, I will sort of rehash some of this stuff and start from chapter 19 and go forward to chapter 20. So these ideas from chapter 19 are where we will stop for this week. And I know it's a lot of content all at once. I encourage you to go back to the lecture segment about the kinetic theory and watch it a few times, and sort of ponder the content and the way we get from premise to conclusion, because I know it's a lot, and we're not done. In in a thermal process, we increase the temperature of a gas. And we'd like to do that at constant pressure. And I'll share my screen in a minute. We'll look at a couple slides for what's going on here. If we're going to increase the temperature, the only way to do that is by changing the molecular kinetic energy. Changing the temperature means changing the average molecular kinetic energy. Okay, the average molecular kinetic energy lived here. If we're going to increase this part of the numerator and keep the pressure constant with the same amount of gas, the only way to do it is to increase the volume as well. That's the only way to do that. So allowing a gas to get hotter at constant pressure means that it is expanding. It's that it is pushing on that its volume has to change. What force is it that pushes on the walls of its container? It's the pressure. We got to this idea from the fact that these molecules push on the walls of the container. Okay, well, wait a minute. If the system, if the gas that we're talking about pushes the one wall of this this setup here, this is a container with one movable wall. If the gas pushes that piston to the right by exerting pressure, a pressure to the force divided by area, the force is directed to the right, that means that the piston is displaced as a result of a force applied. That's work. Whoa, okay. Whoa. Um, we're talking about, let me just draw this really quick. We're going to move through dx, and there's some area. P is pressure times area is the force that's pushing us this way. All right, so the force, so I don't need this diagram anymore. The force that is the work that's done is the force dot the displacement, delta R, I suppose. You know what? Let's do it this way. For some small dr, we can do a differential amount of work according to the dot product. If we want to talk about the total work done, we got to integrate. So hold that thought. The force that's applied is the pressure times the area, and that is directed to the right, which is the same direction as the change of the position of the piston. So the direction dot direction is just the product of the magnitudes. Force times displacement dx, or dr if you like. The area times that distance, that's the volume of a cylinder. And that cylinder is the volume by which the region in which the gas is contained has expanded during this motion. This is the pressure times the small change in volume associated with moving that piston. If you want to talk about the total work done, we've got to integrate all the work. dW. Total work done is the integral of pressure times dV. In this same pressure, constant pressure process, the pressure is not a function of volume. We could pull it outside, and then we're just talking about pressure times the change in the volume from V1 to V2. If the pressure isn't constant, then we got to leave it inside the integral, and this is a perfectly good thing. Our thermal systems can do work. This is perfect. This is what we wanted them to do. Back when we started this whole sort of thermodynamical discussion, we said we wanted to make an engine. We wanted a system that was capable of doing work. And we've just shown that a thermal system is capable of doing work. Let me show you some more pictures. So we've got point 1 and point 2, pressure, volume, pressure, volume. As we go from point 1 to point 2, it's the area under that curve, the integral of P dV, like the integral of F dx. If we go the other way, then we're walking the area, walking the x-axis, the volume axis backwards, and we're talking about a negative area. Here's another example of the process we just talked about. A constant pressure expansion is just a rectangle because we factor out P and then we're just integrating dV, so we get the pressure times the change in the volume. To get from state 1 to state 2, we have many, many, many choices. And these are 3 that are pictured. We could first go across the top and then down. And the work done by the system in that sequence is the total area shown, shaded pink here. But we don't have to do that. We could start at point 1 and go down to point 4 and then across. And the area under that curve is much, much less. There's a third process pictured. We could go sort of on this curve from point 1 to point 2, state 1 to state 2, and this is a different work again. So Now I was so excited. We said that thermal systems can do work, but now it depends how they do it. And that's a strange thing. So pressure and volume, just telling me the beginning and the end is not enough. I don't know how much work was done going from state one to state two because I don't know how we got there. And needing that very, very specific information about how the transition from state one to state two happened means that we're sort of stuck. Um, I really wanted the work done during a process from state one to state two to only care about state one and state two, but clearly that's not the case. So I'm trying to think about something that only depends on state, where we end, where we started. Great, now we know its value. Okay, here's my thinking. Um, the hold on. The internal energy of the gas, though, only depends on the temperature. You tell me what the temperature is, and I can tell you what the internal energy is. And the temperature is related, according to the ideal gas law, to those state variables. So hold on, that's 3/2 NKB. The ideal gas law, PV nRT, so T is PV over little n. You want to use the other one? P capital V N K B T. So T is PV over N. Oh, wait a minute. Ooh, this is cool. All right. So during a small temperature change dt, the pressure and volume might change. Small temperature change dt means a small change in the total internal energy. So du equals 3/2 dPV. And we can integrate, and the pressure volume relationship that we were just talking about, internal energy, temperature. Okay. But what does the temperature have to do with the heat that was required to change the temperature and the work that the system is then capable of doing? This is the piece that we're missing. And to answer this question, we need to talk to James Prescott Joule. James Prescott Joule worked for a beer brewing company, and he was interested in the fact that the cisterns of the silos of beer during the fermentation process changed temperature. He was interested in that. So he did a series of experiments in which he was able to show that And this diagram we've seen once already, that we could change the temperature of a sample by exposing it to direct heating, Bunsen burner or what. That's just the lid of the thing here. Or he was able to show that he could get an identical temperature change, an identical observable result by turning a paddle wheel, by pushing a paddle through the fluid, through the water, by doing work on the water. The actual original setup, I think, it was a crankshaft through the thing, and there was a weight suspended, and as the weight fell, this unwound, and we know what that force is, and we know how much work we're doing, and we can show that there is an amount of work that is associated with the temperature change that is associated with a time. That's, remember how we were talking about quantity of heating is how much time we do this for, that he was able to show that we can get identical results by heating for a time as doing some amount of work. And you know, there was a direct correlation between the amount of time that we spend heating and the amount of work that we had to do. Work is the transfer of energy, right? Because the work energy theorem, the net work done on a thing is the change in the kinetic energy. All right. Whoa, wait. So did we kind of know that temperature and kinetic energy were related already? If we do some work, we change the kinetic energy of the stuff. Changing the kinetic energy of the stuff means changing its temperature. Joule was able to show that doing work to change the kinetic energy is doing work to change the temperature. Changing the temperature then must mean moving energy from here to there. Taking this, whatever this is, burning it, and sending that energy into the sample. We transfer energy into the sample, either by mechanically pushing and doing work, or directly with heating. That's what heat is. It's not a thing, it's a verb, right? We can't find anywhere just a pile of work. We can have energy, and then we can do work. We can transfer that energy to our environment, to some other object. Heat is the same way, and Joule is able to show that, and that's why we named the unit of energy after him. He was able to connect sort of this like physical, mechanistic branch of physics with the thermal branch of physics. Very, very cool. Heat is not a thing that exists just in a pile somewhere. Energy exists in a pile, and we can transfer that energy by doing heat. We say that we're doing work. I'm going to keep saying that we're doing heat. Heat is a noun. So is work. We do work, we do heat, and Joule is able to show that those are related. Okay. So suppose we have a piston in equilibrium with a gas in a container. Right now, everything is in equilibrium, no work is being done. We change the temperature by heating. And the gas, we said a second ago, does work on the piston to move it. Where did the gas get the energy to do that work? From the heating. Suppose we do some heating. We can change the energy of the gas. We can change the energy, and the gas can do some work on its surroundings, on the walls of its container, on that piston, or both. This is the first law of thermodynamics, and it's really just conservation of energy. If we transfer energy into a system by heating, either the energy stays there and becomes part of that system, or it's transferred out by work. Not all of it needs to transfer out. Some of it can stay there. We can do both. But if we transfer some in, either it's still there or it's transferred out. It's basically energy conservation, and because it's basically energy conservation and uses an equality, a relationship between quantity of heat and work done, I credit it to Joule, right? That this equal sign relates heating to work. Turn this around, solve for delta U minus W by the work done by the system. Now, if we push on that piston, if we displace it inwards, the gas is pushing, but it's displacing opposite that. So the gas is doing negative work, minus the negative sign changes delta U. This is okay, so that the internal energy changes, which means the temperature changes. That's what Joule said, that we can change the temperature by doing work on the gas, on the system. The prepositions never mattered so much. Work done by and work done on a system. Really important to keep that distinction. When we're talking about the first law of thermodynamics, I like it with a work done by the system, because that's really what we're trying to do. We're trying to make an engine, and we want the engine to do work for us. This is a really neat thing. And it comes back to the question I just had about state variables and the work done. Q, okay, fine. The work done by the system is different if we undergo a different process. If we go from state 1 to state 2 via one process or another, we end up with a different integral. So this term could be not the same for the same endpoints. It is path dependent. Q it seems like it could also be path dependent because we're talking about two situations, one where we're doing heating and one where we're not. But for both of them, there's a temperature change. And the temperature change is all we need to know to talk about delta U. The temperature change is uniquely determined by the pressure and the volume and the number of molecules. Let's assume we're not losing any. Uniquely determined by the pressure and the volume in state 1 and state 2. If we know PV at both places, we know the temperature. And if we know the temperature, we know the internal energy change, regardless how we got there. That's what's cool about this, is that we're saying the heat might be different. We might have needed to add some, we might have not. The work done might be different. Are we allowing the gas to expand or not? Are we pushing on it at all? But together, those two pieces need to work out well according to energy conservation. Energy transferred in is either energy stored or transferred out. It can't be anything else. But this configuration of it, this is path independent. This left-hand side must be, because it only needs the temperatures. So this right-hand side must be as well. And that's a really special thing. A really special thing. The first law of thermodynamics. Very, very cool. So far, we've seen the 0th and the first. And we just need to talk about the second and the third. Or at least the second. It depends whom you ask, whether there are a total of 3 or a total of 4. But in any case, this is where I'd like us to stop for this week. Now that we have the first law of thermodynamics, what I'm going to do, this is how I will start next week. We'll start here and we'll use this and our kinetic theory model from chapter 18 to say some interesting things about specific heat and molar heat capacities. When we left chapter 17, we were talking about how it's very strange that the molar heat capacities of lead, aluminum, copper, and all this stuff were so similar when their specific heats are so different. And we can get at that idea now that we have this and the kinetic theory. Now that we have the first law of thermodynamics and a definition for the work done by a thermal system, we can start to characterize thermal processes, allow some amount of heating to occur and see what happens, and talk about how much work is done during this kind of thermodynamic process or that kind. And that endeavor is part of our recitation this week. So that's why we had to sort of squish chapters 17 and 18 into this first week of thermodynamics. I know it was a lot. Please email with any questions, jump in the Zoom chats, make office hours reservations, or all three. But yeah, that's enough for now, I think. Take care, everybody. Be well.